Okay, hello, welcome to an introductory lecture on kinematics, which is a fancy way of saying the study of motion, right? That prefix kine always means motion. We have been investigating the fact that forces, or more specifically the net force, will cause you to accelerate, right? Which is a kind of an abstract concept, but we know that that acceleration is defined to be the change in velocity, the rate of change in velocity. And velocity, of course, we know is how quickly you're moving through your positions, right? How quickly your position is changing. So what we want to do is we want to codify and relate those variables a little more carefully and explicitly. So the first thing is to distinguish between words that people use interchangeably in everyday life that are really not the same thing, right? We've talked about this before, that there are two kinds of mathematical objects. There's scalars, which are just the numbers and all the number theory and algebra that you do up until about pre-calculus, I guess, in the math sequence. And those are numbers that just have magnitudes. They're not associated with directions. And in physics, we like to use vectors. Vectors are numbers that actually have a specific direction in space so that you can think of them as arrows, right? In fact, that is the right way to think about them. And we signify that a variable is a vector by drawing a small arrow over it. So for instance, these two words, displacement and distance, people will use interchangeably, but the distinction is this, is that distance is technically always a positive number. It's just the amount of miles you've walked that day. It doesn't matter what direction you go. Whereas displacement represents an arrow that connects your starting position to your ending position. So if you do any kind of round trip, your displacement is zero, right? And the positive and negative signs have directional information, right? Positive meaning, going to the right, negative meaning going to the left, that kind of thing. We're going to be very formal and explicit about vectors in the next unit. So velocity and speed play similar roles in that speed is the magnitude only version. So technically speed should always be a positive number because there is no direction associated with speed. And velocity, on the other hand, is directly defined in terms of displacement. So if you have a zero net displacement, then your average velocity must also be zero, right? Because velocity is defined to be the rate of change of your displacement. For speed, you'd find your average speed by calculating the total distance you've traveled and dividing by the total amount of time. And that can be, as we'll see in a minute, a completely different answer. Acceleration is, of course, what we've been talking about. The net force causes acceleration. That's the effect on your motion that forces have. And that is the rate of change of velocity. And the other kinematic variable is time, of course. So time is a scalar. You can think about yourself as going forward and backward in time, but that can't be represented as an arrow in three-dimensional space, right? Just a little as an aside, Einstein eventually is going to put all these things together and say that time is just the fourth dimension, whereas displacement has three dimensions. So the right way to think about it is x, y, z, your three dimensions of displacement, comma, t, and your fourth scalar component is time. But that is for another day. All right, so one thing to note here is we have about four distinct variables. We'll mostly write equations in terms of five variables. The five variables being the time you've been traveling at a constant acceleration, so t and a for time and acceleration. During that constant acceleration interval, you have had a total displacement, so your displacement d would be your third variable. So we've got time, your time interval of the constant acceleration, those are two values. The displacement that you experienced during that time interval. And then your velocity, of course, was always changing, so we usually will talk about an initial and final velocity, right? Your delta v, your change in velocity is defined by your final and your initial. So those are your five kinematic variables, t, a, v sub I for initial velocity, v sub f for final velocity, and d displacement. Well, before we look at the equations, let's just think about these. All right, so here's an example problem. Let me read it to you, and then if you're watching the video, you can just pause and think about your answer before I give you the answer, what I think is the correct answer. So I'm going to define a lap to be across and back. I always get confused whether that's just across or just back, but it seems like most people think a lap is there and across and back again.
So if it's a 50-meter pool, so that would be 3 laps would be 100 meters plus 100 plus 100. So it's 300 meters total. Which of the following pair of numbers represent the distance, comma, displacement you've gone? All right, so why don't you pause here and commit to one of these answers. Okay, hopefully you did pause and commit to an answer. That's an important part of having a dynamic relationship with the lecture, is to be thinking about these questions as you go along. All right, that's the last time I'll admonish you. All right, so distance is what I said earlier, right? That's the 300 meters. You just add up the total number of meters you've traveled, and so that would be the first number in the answer should be a 300. Now your displacement is technically 0, right? Because every time you do a complete lap, it's like going around the track or like leaving your house in the morning, coming back to your house at night. You draw an arrow from start to finish, and the arrow has no length, right? It has no magnitude. You haven't actually gone anywhere overall. There's been just as much positive displacement as there was negative displacement. So the correct answer here is letter C. So when we're talking about positive and negative, I want to make this tangible, right? If we're in one dimension, a positive displacement doesn't mean that you are on the right-hand side. It means that your arrow is directed towards the right-hand side. So for instance here, if you move from the position 10 meters to the position 30 meters, your final is 30, your initial is 10. And the delta sign always means final minus initial. So 30 minus 10 gives you a positive number. So that's how you get positive 20 algebraically. What it means representationally is that the arrow is pointed to the right. Notice that blue arrow is pointed to the right. On the other hand, if you go the opposite way, if you start at 30 and go to 10, now when you go to find the change in displacement, it's a 10 is your final and your 30 is your initial. So you get 10 minus 30, you get a negative 20, right? So what does that negative sign mean? It means that the arrow is pointed towards the left, right? The 20 in both cases is the length of the arrow. That's the magnitude part of the vector. And the plus or the minus sign is showing you the direction of the arrow, right? And that's true for all velocities. I'm sorry, all vectors. So I think I said this earlier, but I'm just formalizing it, right? Speed is always going to be a positive number because technically the distance you've traveled is always positive because those are both scalars. You take the total distance you've traveled divided by the total time you took, and that will give you your average speed for a trip, right, for a certain time interval. Velocity is a little tighter because it has direction information, so you find your net displacement over a time interval, divide by that time interval, and that will give you your average velocity, right? And negative sign means something about direction. So let's do the same problem, but let's put some time in here. Same distance, displacement, and you did it in 2 minutes. So which of these pairs of numbers represent your speed, comma, velocity for the trip? Obviously, it's been rounded. All right, so pause here, think about it, commit to an answer. All right, so we already know the distance, comma, displacement was 300, comma, 0. So those are the two numbers we now need to divide by, not 2 because that's minutes, and they want it per second, so that would be 120. So I've got 0 divided by 120. I can do that easily. That is 0. So the velocity will be 0, right? That's your average velocity for the whole trip. And then your speed will be the 300 meters divided by 120. So that's going to be 120 is 240. So it's 2.5. Yeah, somewhere around 2.5, right? That must be what it rounds to. So that would be letter B. Now, how can you have an average velocity of 0 when you're moving all the time? Well, when you're going one way across the pool, you have positive velocity. And then when you're coming back the other way, your arrow representing your motion would be in the opposite direction. So you have as many arrows pointed to the right as you have pointed to the left, and they cancel out. I've been using these words, but let's define them a little more carefully, and then I'll show you what it means graphically. And your instantaneous value is your value at an instant in time, right? So you don't care what you were doing 1 second earlier or 1 second later. It's just like, how fast are you going right now? You can talk about instantaneous speed. You can talk about instantaneous velocity. You can talk about instantaneous acceleration, right? Any of the kinematic variables, you can have an instantaneous value, your instantaneous position, right? The average, you need an interval of time. So what does this look like graphically? So I've just made up a little graph here, this black line, like somebody's walking back and forth, in the park or something like this. And this is their distance from an origin. So the y-axis here could be called distance, it could be called displacement, it could be called position, right? Because you can get directional information out of this, so it doesn't really matter what you call this. Usually it'll be called position. But your position, of course, is a distance from a specified origin. And of course, at that moment in time, that's also your displacement from that origin if you think about walking from the 0 point to that point in time. So that's why there's a lot of kind of sloppiness and synonyms for the y-axis here. But basically, if it's done in meters, then the slope on this graph is going to be delta x or delta d over delta t. So that means the slopes on displacement or position or distance versus time graphs, those slopes are velocities. And positive values are positive slopes, meaning you're going forward, and negative slopes are negative values, meaning you're going backwards or you're going in the negative direction more precisely. So here the blue arrow is representing the average for the whole trip, right? Just connect the starting point with the ending point with one straight arrow. That would be your displacement. Divide it by the time. That would give you the slope of this blue line, and that would be your average velocity. On the other hand, you can pick any moment in time in here, and they will all have kind of, I drew this so it looks like the slope is changing constantly, right? You'd have some positive slopes here. You'd have some negative slopes along here. I drew in red arrow at this point in time. And so what you do, if you don't have straight lines, is you kind of freehand an arrow that is tangent to the curve at that point, right? So it's kind of like if you were to blow up that area of the curve, it's like a mini straight. Every curve is made up of, mini straight lines if you blow it up big enough. And you take that small straight line and you expand on it so it's large enough for you to actually measure the slope. And that would be the instantaneous velocity at that point in time, which is a positive value, but you can see the steepness of it is different than the blue arrow. Right, so here's a tangible example. If this red line is your motion graphed over time, your positions as a function of time, I could take the slope. Since this is a straight line, the slope anywhere is the slope of the whole thing. All the instantaneous slopes are equal to the average slopes. So they're taking two arbitrary points here, and they're finding the rise being 11 and the run to be 1. And so that means you have a velocity of 11 meters per second in this problem, right? So when you go from 0 to 4, you'd expect to go 44 meters. Yeah, that looks about right. Okay, just a little bit of reminders about calculating slope. So if this is a position versus time, this is actually taken from a homework problem in the book. What is your average velocity from A to E? So here at A, we're at 0.25. At B, we're at 0.15. Why don't you pause here and calculate the slope and commit to your answer? Okay, so I would say if you're going from 25 to 15, that's a delta x of negative 10, right? Because it's 15 minus 25, so it's negative 10. You're also going backwards towards the origin, so that's another way of looking at why it's negative. And then I need to divide that by the delta t, which is 6. So negative 10 divided by 6 is like 1 2/3, so 1.7 to 2 sig figs. So a negative 1.7 meters per second. Right? I need the negative sign to indicate direction because it's asking for velocity. I need the units, meters per second, which I'm picking up from the axes here. And I'm kind of respecting sig figs by saying 1.7. If I were to say 1 2/3, that would imply infinite precision, and that would probably annoy your physics teacher. There's no way anybody measured your position or time with infinite precision. In fact, according to the Heisenberg uncertainty principle, it's not possible. So take that, math people. During which interval of time is the velocity negative? All right. So you have to commit to one answer here. So let me pause. Why don't you pause and commit to an answer? All right. So from C to D, you've got 0. From D to E, you've got positive. All of these points have, A starts off 0 and then quickly becomes negative, right? And so you can imagine it's already starting to get a little bit negative here. And then we have negative slopes all the way. Now the slope is changing, and sometimes it's constant, but between A and C, it is always negative. So I would say that the best answer is A to C. Some people may be bothered by it's a little bit 0 over here. So, maybe from 0.5 seconds to 2.5 seconds would be the cleanest answer. But of these choices, A to C is the one that I would choose. What is the average velocity from A to C? So now we're supposed to calculate it. So why don't I pause and you guys can see what you think. All right, so I'm going to do 25 down to 5. So that's a negative 20 displacement divided by delta t looks like it's around 2.5. So I've got negative 20 divided by 2.5, and I don't have a calculator on me, so whatever that is, let's see, 12? 12 sounds about right. So somewhere around negative 12 meters per second. I'm sure if I got that wrong, people will email me. It's the process, people, not the answer, right? We've got a rise of negative 20 and a run of 2.5. So we definitely have a slope that has units of meters per second. Okay, now we can also graph these velocity versus time graphs. People have a lot of trouble with this because people are used to seeing displacement or position versus time graphs, but you can, of course, also measure your velocity at every instant in time and then graph that, right? Or it could be speed. Once again, people are a little bit sloppy in labeling the y-axis, but if you have units of meters per second here and you have units of seconds there, then you can figure out what the slope would be by doing rise over run, so meters per second, which of course is the original definition of acceleration. So slopes on velocity versus time graphs are accelerations. And you can play the same game about having instantaneous slopes, like that's what I'm showing you with the red arrow, is the instantaneous slope at that instant in time. So that's what my acceleration is right at that moment in time. I could also do an interval of time, right? Like if I wanted to go from here to there, I would connect those 2 points with one straight line, and I would find my average acceleration would be the slope of that straight line. Now there's another trick you can do on graphs, which is you can find the area under the curves. And sometimes that has a physical interpretation, sometimes it doesn't. And like the slopes, you can use the units to tell you whether it has a physical interpretation or not. So you can imagine this blue area here is made of a whole bunch of little squares on graph paper, if you were to graph this. And each one of those squares would have an area equal to what in terms of units? Well, it has a height of meters per second and a width of seconds. So to find the area, you multiply those. What do you get when you multiply meters per second times seconds? You get meters. And so meters are the unit of displacement. And so the area under the velocity versus time curve gives you units of meters, which are the units of displacement, and that's what it means physically. If you go back to a displacement versus time graph and find the area in one of these squares, what you get is you get a meters times a second. So you get a meter second, which doesn't correspond to anything physical and therefore doesn't have any meaning. You can calculate it mathematically, but it doesn't correspond to a kinematic variable, right? The units, by the way, the right way to do this is not to memorize what does the slope mean on these type of graphs, or what do the areas mean on these type of graphs. That's the hard way to go through physics, right? You got to go at the underlying principle here, people, which is that the units tell you what the physical meaning is. And you should just know, oh, slopes and areas are interesting in graphs now that I'm a big kid. And so you know that the units will tell you what the slope and the area means. All right, so here's a question. I've got a velocity versus time graph. At which of these times is the acceleration negative? Right, so just look at those instantaneous values and decide. So pause here and commit to an answer. Okay, there really are only two intervals here where we have negative accelerations, right? We have positive accelerations here because they're positive slopes, then 0. Then here's one interval that's negative. Then we have a 0, and then here's another interval that's negative. This interval is so small, I'm hopeful that they didn't put some number like 0.49 anywhere, and I don't see that, so that's good. So I don't have to, 0.45 is clearly still over here in the flat area. So that means hopefully one of these intervals is somewhere just under 0.2. Maybe even just beyond 0.2. I don't know, a little bit hard to tell, but when I look over my choices, letter C stands out. 0.19 would be about right here, and that would be in the middle of this negative slope area. Okay? Which of the following is a reasonable expression for the instantaneous acceleration at the 0.02 second mark? All right, 0.02 would be about a fifth of the way from here to here, so about right there. Why don't you pause and commit to an answer? Okay, now if you chose A, you have done a classic mistake of reading the graph rather than answering the question, right? If the question were, what is your velocity at 0.02 seconds? Maybe 30 might be a reasonable answer, right? Maybe you're up here. But that's your instantaneous velocity, which is not what they're asking for. They're asking for your instantaneous acceleration, which is not reading the graph, it's finding the slope on the graph. And so anywhere between 0 and, say, 0.05, whatever time that is, though that's a straight line that has a positive slope. All of those instantaneous slopes would be the same as the average slope in that interval. So I don't really need to monkey around with exactly where 0.02 is. I just need to identify what straight line it's on and then find the slope of that straight line. So to me, that looks like it's going up 50 and over about 0.05. So if I do 50 divided by 0.05, I'm going to get about 1,000 kilometers per hour for the rise, per hour for the run. So that's the kilometer per hour squared. And I'm going to go with letter C. If I had a curve, it would be a little bit harder, right? I'd have to draw the straight line myself, as I explained earlier. Draw your best tangent line. I'm unlikely to ask you numerical questions about slopes on curves, but I could ask you if it's positive or negative, if it's decreasing or increasing, those type of questions. Now, acceleration versus time, if you were to find the slope on that, you would get meters per second per second per second, or meters per second cubed, which is not something physicists normally talk about. It is actually defined. I think it's defined as the jerk, actually, right? So if you experience a change in acceleration, it'll cause your body to jerk around. I think that's where the origin of it. I've had math teachers talk about it, but I've never had a physics teacher talk about it. As I said earlier, we stopped the game here at acceleration because physically that's what forces cause. And so what we're trying to relate is, of course, the kinematics to the forces. However, the area here does mean something, right? If you find the area of this blue square, you're going to get a height of meters per second squared and a width of seconds. So what do you get when you multiply meters per second squared times seconds? You get meters per second, which is the unit for velocity, right? Curves above the x-axis are considered to have positive areas, so that would be increases in velocity. If your acceleration were to go negative and be down below, then you would have areas below the x-axis. Those are considered negative areas. Not a real thing, I guess, in terms of areas, but as a concept, right, it's a negative acceleration. So those would be decreases in velocity, delta v's that are negative. So if you have constant velocity, there's basically three flavors of constant velocity you could have. You could have a constant positive velocity, which would give you a distance versus time graph that had an upward slope, straight line. You could have a constant velocity of 0, which gives you a flat line in position versus time. Or you could have a constant negative velocity, right? So going forward without speeding up or slowing down, standing still without speeding up or slowing down, going backwards without speeding up or slowing down. And what does that look like in displacement versus time? Nice positive slope, nice horizontal line, nice negative slope. What if you have constant accelerations? Well, for the first 70 seconds or so on this graph is just a repeat of the previous graph, right? Just because I have 0 acceleration doesn't tell you anything about the value of velocity. It just tells you it's not changing, right? So this isn't quite physical because to change from 1 meter per second to 0, from 0 to -1, there obviously would have to be some kind of blip in acceleration here. But this isn't actual data. I just made this graph up, right? This is like something you'd see in math class with sharp turns and instantaneous changes, right? Very unphysical. But what's new here is now I put in a positive acceleration. So what does that mean? That means I need to have a line in velocity versus time that has a positive slope. And since I have a positive slope here, that means my velocity is positive and increasing. That means I need a position or distance versus or displacement versus time graph that has an increasing slope. That has to be a curve, right? And this is a curve that starts small and positive and is getting steeper and steeper and steeper. So that would correspond to that straight line. Then I drop here to a constant negative acceleration. So what does that mean? That means that I need to have a velocity that has a negative slope. It didn't have to be negative values. I don't know why I chose to drop it down here to negative values. It just has to have a negative slope. And so having a negative slope here means I need to have a downward slope in position versus time, and it needs to be getting steeper and steeper, bigger and bigger negative number, right? And then I popped up the value up here to show you that that is still a negative acceleration, right? So as long as this slope is the same as that slope, it will actually have the same value on this graph. Once again, there's something unphysical happening around the 125th second or so, and that there needs to be some kind of weird spike to reset the velocity. And now I have positive but decreasing velocity value. So notice that this curve is curving the opposite way of that curve. These all have positive velocities, and these all have positive velocities. But the difference is these are positive velocities that are increasing as that becomes steeper, And these are positive velocities that are decreasing as it becomes flatter, right? And then the last interval is a positive acceleration with a negative velocity, right? And so I need negative velocity, so I need to be going downward, but I am going towards 0, which means I'm getting shallower and shallower, right? So you get curves, which are quadratics, when you have constant non-zero accelerations. So in this one graph, I see what I've done now. This is why I made it unphysical, because I wanted to cover all the cases, right? Positive acceleration, positive acceleration, positive velocity gives you this. Negative acceleration, negative velocity gives you this. Negative acceleration, positive velocity gives you this. Positive acceleration, negative velocity gives you that, right? So no matter what, you get curves here, straight lines here, flat lines here. And constant acceleration is what we care about, because any free body diagram represents a constant acceleration for a small enough interval of time, right? So even when you have complicated forces that are changing dynamically, if you take a snapshot in an instant in time and draw a free body diagram, you can pretend like you have a constant acceleration in that moment in time, and then connect it if you need to connect it to another moment in time where you have a different acceleration. Then you just start and stop the whole process over and over again. So this is just a blow up of the classic case. A constant positive acceleration will give you a nice straight line with whose slope value here is this value. Since these values need to be your slopes here, you need to have a curve, right? So you have a quadratic, a linear, and a constant function. This is the most common situation that we'll see in physics. It's so common, right, to have constant acceleration that instead of analyzing it graphically, we can use our knowledge of graphs to actually construct some equations. So the first one would be to relate velocity. This is a straight line, so let's just use y equals mx plus b, right? So here's my y, I'm graphing velocity on the y-axis. My slope is the m, is the acceleration. My x-axis is time, so this is my y equals mx plus b. What is b? B is your intercept. That is your value at time equals 0. So that's what I would call my initial velocity. Now, let's use the trick that the area under this curve should be telling me something about our total displacement. And now I can figure out what this quadratic function is, right? So this is a triangle underneath the blue here. So I'm going to do 1/2 base times height. Here's my 1/2. My height is acceleration times time. And my width is the second factor of time, right? So I've got 1/2 at times t. That's the 1/2 at squared. So that will give me the area of this triangle. And now if my starting velocity was not actually 0, then I'd actually have to draw a little rectangle here and find the area of that. That's easy to do. The width of that rectangle is t, and the height is my velocity initial. And so in general, here are the two equations of motion. This one governs velocity as a function of time, and the bottom one is displacement as a function of time. So there really are only two kinematic equations. Now, when you look them up, and even later I will show you, I'll give you a handout, you'll frequently find lists of 4 or 5 different equations of motion. But they all come from these two: velocity as a function of time and displacement as a function of time. What it is you can just solve this one for t and substitute it in there. You can eliminate time entirely, right? You can play games with these two equations depending on what unknown you're anticipating seeing, right? So the name of the game is this. You have two equations and you have 5 variables, right? The a, the t, the initial velocity, the final velocity, and the displacement. Those are your 5 variables. And you have 2 equations. So if you have 5 equations, 5 variables and 2 equations, that means every solvable kinematics problem must give you 3 numbers, right? 3 pieces of information, 3 numerical values must be specified in order for you to solve for the other 2. If you get a kinematics problem and they don't give you 3 numbers, then it's not a solvable problem, or you need to reread the problem. Maybe you missed something.